Hello and welcome to Chemistry 101 again. This is your instructor, Dr. Ismail Badran from Qatar University, and today we are going to start Chapter 3, which is mass relationships in chemical reactions. So after we went into a journey into Chapter 2 and knew how to name compounds and how to do the naming of the compounds, now we are in Chapter 3 and now we're going to dig more into chemistry and acquire more skills in order to master chemistry. So this chapter includes very important topics like the atomic mass and the molecular mass and the idea of mass percent. We will also learn how to solve chemical problems using different techniques, and it's going to be fun to do this chapter. The first thing is we need to talk about the atomic mass itself. So what is the atomic mass? Can we weigh an atom? It's not practical weigh an atom. The atom is too small, so you cannot put it in a balance or scale. You can't even see it. So the idea of atomic mass came from a definition that scientists agreed that one atomic unit or one AMU is the atom mass is the mass of one atom of carbon. So this is the idea here, is that everything in the periodic table is based on carbon. So we gave carbon atomic mass of 12. Okay, and as you know, the carbon has more than one isotope. So there's the carbon 12, 13, and 14. So we took the carbon 12, which is the isotope of carbon 12, and we defined the atomic mass to be 1/12 of the mass of one carbon atom. So based on that, we related all the masses in the periodic table based on that. So by definition, we have one atom of carbon that weighs 12 AMU. So 1 AMU is equal to 1/12 of the mass of one carbon 12 atom. Meanwhile, we defined all the other elements based on carbon. So hydrogen 1, for example, the isotope of hydrogen that has one atomic mass is equal, the mass of it is 1.008 AMU based on the carbon. And oxygen is, let's say oxygen 16 is 16.00 AMU. So all the other elements, they have atomic mass is based on carbon. So as you see in the periodic table here, carbon has an atomic mass of 12.01. So this is of course the average atomic mass, because you know carbon consists of more than one isotope. There is a carbon 12, carbon 13, carbon 14, and so on. Carbon 12 consists most of the carbon in nature. It's almost 99%, and specifically it's 98.9%. Carbon 13 is 1.1%. And when we do some calculations, we obtain this number 12.01, which is the average atomic mass for carbon. So here in the periodic table, if everything you see in the periodic table, let's say Cl has an atomic mass of 35.45, that's the average atomic mass between different Cl atoms. Here is an example to calculate the average atomic mass. The example says boron is used in the manufacture of ceramics and polymers such as fiberglass. The atomic masses of the two stable isotopes, B10, which is 19.8%, and B11, which is 80.2%, are 10 point something and 11 point something AMU. So we're given two isotopes of boron with their natural abundances, and also we have their exact masses. The boron 10 isotope is also important as a neutron capturing agent in nuclear reactants. Calculate the average atomic mass of boron. So this is a simple question. I just organized my work here. I have boron 10 and boron 11 in the table, and I have the percentages in nature, 19.8%, and that was saying 19.80, and 80.2%, and we have also their masses and their exact masses. So basically, boron 10 has a mass of 10.0129 AMU, and the boron 11 its exact mass is 11.0093 AMUs. If you ever want to calculate the average atomic mass of the element, which is the average atomic mass, you just do simple calculations. You multiply this number by this and multiply this number by this, and you add the of boron will equal to first of all 10.0129, the first number, and then multiply it by its percentage. So you can do that either by dividing by 100 or converting this into a decimal. So you can do it 19.8 divided by 100 like that, plus the other one, which is 11.0093 AMU, times the percentage, which is 80.2 divided by 100, and you close that bracket. So you can do this math, and you will obtain a number. You obtain a number of 10.8 12 AMU. Notice two things here. First, the average atomic mass is more close to the 11 because of the fact that it is more abundant in nature. Another thing is, if you compare this number to the one in the period table, they should be similar. 10.812, keep this in mind. Let's go to boron. Boron is right here, 10.811. It's almost close to that number. Okay, so we're done with this. Okay, this is the question here. We're done with the question. Moving on, as we said, this is the average atomic masses. All the period table, the numbers in the period table shows the average atomic masses because they are averaged between different isotopes. Some elements actually make a lot of isotopes, like silicon and phosphorus. They have a lot of isotopes. So when you say phosphorus is, the atomic mass of phosphorus is 30.97. I'm expecting that there are phosphorus 30, phosphorus 31, 32, and so on. But of course, their masses and their natural abundances are different in nature. Okay, now so moving on. Now we're going to talk about the mole and the concept of mole, which is a widely used concept in chemistry. If you're ever asking what is a mole basically is a number. So as you see here in this funny picture, if you have mole problems, call 6021023, which is relates to the Avogadro number. And Avogadro number is huge. It's actually equal to 6.02 times 10 to the power 23. So that's a big number, and it's just a number as any other number. So for example, if you say dozen of eggs, that would be 12 eggs. If you say 1 kilo of eggs, that would be 1,000. And therefore 1 mole of eggs, that would be 6.02 times 10 to the power 23 of eggs. But in chemistry, mole plays more than just a number, because the mole in chemistry is the amount of a substance that contains as many elementary units, for example, atoms, molecules, or formula units, as there are atoms in exactly 12 grams of carbon. What does that mean? Basically, that we define the atomic mass of carbon to be 12, and therefore 1 mole of carbon would be equal to 12 grams. And that's a very important relationship in chemistry. So the Avogadro number is referred to Na here, N subtract A, which is again equal to 6.022 times 10 to the power 23. It's a huge number, of course. So for us, the molar mass, we define the molar mass as this. If you have carbon, let's say again, and the carbon is 12 AMU, then 1 mole of carbon will equal to 12 grams, basically. That's just as this. Take another example, which is sodium. If you look at the sodium in the period table, the atomic mass of sodium is 22.99 AMU, and therefore 1 mole of sodium will basically equal to 22.99 grams, almost 23 grams. So if I ask you in the lab, go and get a mole of sodium, you will just go to the balance and you weigh 23 grams, and you say this is equal to 1 mole. If you need 2 moles, you just multiply that number by 2, and you bring 46 grams of sodium. Here is a picture of different elements. We have here carbon, which is basically charcoal. We have sulfur, the elemental sulfur, of course. We have also iron and copper. In the middle, we have some mercury, Hg. This picture, actually, what happened is that we weighted exactly 1 mole of each substance. So we have here 1 mole of carbon, 1 mole of sulfur, and 1 mole of mercury, and so on. But their masses are different, because if you look at the periodic table, for example, the sulfur is 32 grams. Is 32. The atomic mass of sulfur is 32 AMU. So 1 mole of sulfur will equal to 32 grams. But if you go to mercury, mercury has an atomic number of 200.5, and therefore we have to weigh 200.5 grams of mercury, and because the mercury density is too high, that will bring a small volume of mercury. So here is the thing that you understand, that 1 mole of substance contains the same number of atoms. So in each of these elements, you have the same number of atoms. Okay, so 1 mole of sulfur, that means you have 6.02 times 10 to the power 23 atoms of sulfur. and that applies the same for carbon and all other elements. For 1 mole of carbon, you have also 6.023 times 10 to the power 23 of carbon atoms, Avogadro number of carbon atoms, and you have also a Avogadro number of iron atoms and so on. But their masses are different. These atoms, because simply these atoms are different in size and they are different in mass. So here's another example. Helium is a valuable gas used in industry, low temperature research, deep sea diving tanks, and balloons. How many moles of helium atoms are in 6.46 grams of helium? So this is another question asking how many moles of helium are in this grams of. Okay, so here's the example 3.2. We are given 6.46 grams of helium, and we are asked for the number of moles. You can do this two ways. There is a formula that says number of moles equal mass divided by the molar mass. Okay, so because he's asking about the moles, you can just write number of moles is equal mass divided by molar mass. That means the mass is 6.46 grams divided by the molar mass of helium, which is equal to atomic mass, because it's an element. In this case, the molar mass is equal to the atomic mass, which is 4.003. So just divide this number by this, and this is gram per mole, and that the gram goes with the gram, the moles goes up, and that will give you 1 point something. So that's almost 1.1379. That's a calculator answer. If you're considering how many significant figures we are giving here, we are giving 3 significant figures. Okay, this number 4.033 has more, so I am doing division. So I will stick with 3 significant figures, and therefore my answer is 1.61 mole. You can call this method A, if you like. If you want to use unit analysis, in unit analysis, what you do is you bring the grams that is given to you. So you say I need the number of moles of helium is equal to something, so 6.46 grams, and then you multiply by something that will give you moles, basically. So this conversion factor, you can say that you need 1 moles in the top, in the numerator, so you put 1 mole of helium, and here you can say that 1 mole of helium weighs 4.003 grams, right? So this grams goes with this gram, and you are left with moles. So basically you divide 6.46 divided by 4.003, and you get the same answer. So these are the two methods to solve these questions. Now we need to talk about something called the molecular mass, or basically the molar mass. The molecular mass basically is the sum of the atomic masses in AMU in a molecule. So for an atom, for an element, the atomic mass will equal to the molar mass. But for a molecule, you need to do some mathematics to do that. So let's say for a molecule like SO2, sulfur dioxide, you have 1 atom of sulfur. Its mass is 32.07 AMUs, and you have 2 atoms of oxygen, each one is 16. Okay, so you multiply 2 by 16, and then you add that to the sulfur, and that will give you 64.07 AMU. In other words, you have 64.07 gram per mole. Okay, so that means each 1 mole of SO2 will weigh 64.07 grams. So remember, for any molecule, you have the molecular mass is equal to the molar mass in grams. Okay, so 1 molecule of SO2 is 64.07 AMU, and that's equal to 64.07 grams. Here is a question that says methane is the principal component of natural gas, which Qatar is rich of course. How many moles of CH4 are present in 6.07 grams of CH4? Again, we can do this easily. So this is example 3.6. It's talking about methane. Okay, and we have here 6.07 grams, or 6.07 grams. This is given. Okay, and the question is asking about how many moles. So again, number of moles of CH4 is unknown. So you need the molar mass. So the solution for this question, you can say the molar mass of CH4, you can calculate that quickly. Carbon is 12.01, let's say, plus you have 4 times 1. Let's just here round our answers. So that will give you almost 16, okay, 16 gram per mole. That's the atomic mass of methane, the molar mass. And therefore you say the number of moles of CH4 is equal what is given to you, 6.07 grams of CH4 times, now here this is something that is really important. This this thing 16 gram per mole, you can write it down as 16 gram divided by 1 mole, or 1 mole divided by 16 gram. For this question we need the grams to go with the grams, so I put grams in the bottom and 1 mole is on top. So this grams now goes with this grams, and basically you divide 6.07 divided by 16. That will give you 0.37 or more. That will give you 0.379. Now there is something called molecular mass and there is formula mass. Remember that compounds, they are divided into ionic compounds and molecular compounds. For molecular compounds, we can the mass we are calculating, it's called molecular mass, or basically molar mass. But if you are dealing with an ionic compound, remember ionic compounds, we only take the unit cell, okay? For NaCl we just take 1 unit and we call it formula unit, and therefore the mass we calculating for that, it's called formula mass. Basically they are the same thing, but it's just because ionic compounds are different in the way we deal with we don't usually use the concept, the word of molecular mass for ionic compound. We say the formula mass. So we say formula mass of NaCl is so and so. So again, this is NaCl. NaCl is composed of many atoms, but here we don't count all the atoms. We just take the simplest ratio between Na and Cl, and we say the formula mass of NaCl is equal to the mass of Na, which is almost 23, and then plus the Cl, which is almost 35.5. And when we add this up, we come up to 58.5 or 58.44 to be exact. So that's the formula mass of sodium chloride. Again, the unit for this, it's either 58.44 AMU or 58.44 gram per mole of NaCl. So how do we actually measure the atomic masses? We measure the atomic masses using a device or an instrument called mass spectrometer. The mass spectrometer is a modern picture of a mass spectrometer, which comes in different shapes and different sizes and different applications. But the idea here is we inject a sample of the element that we need to study. Let's say carbon. In this case, we inject actually neon, and from the right side. And then that sample will go through different optics and different magnets, and it's going to go through a big magnet, and that magnet basically will pull the isotopes apart. So it will basically separate the isotopes from themselves. You know, helium, for example, if you introduce a sample of helium, that's not going to be only one isotope of helium, but it's more than one isotope. So the magnet will separate the isotopes, and you will detect them at the end, as you see here to the right in the detection screen. So the light isotopes will go to the left, for example, and the heavy ones will go to the right. So this will project in what we call a mass spectrum. So here in this slide is a zoom into the mass spectrum of helium, and as you see here, this mass spectrum is composed of mainly 3 peaks, one big and large and nice peak at 20. That's for helium-20, which is the isotope of one isotope of helium, and that the height of the peak is almost 90.92%, so almost 90%. There's a small peak at 21, so that just tell you that neon 21 is not that much in nature, and you have a smaller peak at 22. So the neon 22 is 8.82%, almost 9%. So from this, you can tell that the neon is composed of more than one isotope. It's not only neon 20. And you can do some calculations here. You can multiply the percentage times the mass of each isotope, add them together, and you will get the average mass of of helium. And finally, in this lecture, we're going to introduce something called the percent composition, okay, or the mass percent. The percent composition is an important topic in chemistry that we'll use to solve problem. And we started with saying by saying how much oxygen in percent are there in water molecule. Now we know that in water we have 2 atoms of hydrogen and we have 1 atom of oxygen. And here we define the percent composition by mass is the percent by mass of each element in a compound. And basically it's N, which how many elements we have, times the molar mass of the element divided the total mass of the compound times 100%. So to illustrate that, we have, let's say here we have water, and the water we know that it's composed of 2 hydrogens and 1 times oxygen atom. So the mass of hydrogen is almost 1, so 2 times 1, and this is 1 times 16. So I here have 2 and I have here 16. I know the molar mass of H2O is 18 gram per mole, right? So 1 mole of H2O is 18 grams because 2 plus 16 is 18, and therefore we can come here and say the mass percent of hydrogen is 2 divided by 18 times 100%, and this will equal to 16 divided by 18 times 100%, and this will give you almost 0.11. This will give you almost 11.1% for hydrogen, and that will give you here 88.9% for oxygen. Notice here that even we have only 1 atom of oxygen, it composes most of the water by mass because of the fact that the oxygen is just heavier than hydrogen. So this is called the mass percent, okay? The mass percent of oxygen in water, or the mass percent of hydrogen in water. We're going to use this in our chemistry. Here's another example for ethanol. Ethanol is C2H6O. The molar mass of ethanol is calculated to be 46.07 gram per mole. So you can do some math that is similar to the previous question. Carbon is 12, hydrogen is 1, oxygen is 16. You can replicate these numbers if you like, and you will find that most of ethanol is actually carbon. It's 52.1%, and hydrogen is 13%, and oxygen is 34%. Whenever you do these calculations, just make sure that they add up to 100, okay? To 100% when you do the mathematics. Okay, so this is about it for this lecture. Next time we're going to talk about empirical formula and how we're going to use the concept of mass percent to account for empirical formulas and a molecular formula. So it's going to be more fun next time. Bear with me, and so thank you so much for listening for this lecture, and have a great day. Thank you.